Okay, I can see we're live. Okay, I suggest we start. Maybe Nina, if you just close the video. Thanks. Great, so welcome all. This is another edition of the One World YoungStats webinar series. YoungStats and the One World YoungStats is a project taking place in the framework of Young Statisticians Europe of the FinStats Association. It is formally supported also by the Bernoulli Society for Mathematical Statistics and Probability, as well as the Institute for Mathematical Statistics, IMS. So today we
don't have other stats, right?
Please, I ask you to close your mics. Somebody, thank you. So today we have fortune to have speakers again and discussant. The webinar is on the topic of non-parametric inference based on statistical depth. The notion of center of an object, be it a set of observations, a physical object, or a random variable, is difficult to define. This motivated the development of general ways to measure centrality via depth functions. Such mappings allow for comparing relative centrality of two locations and consequently providing a center outward ordering. Many such mappings have been introduced in the literature in recent decades, and this is subject to intense research in most frequently non-parametric statistics and functional data analysis. So in today's webinar, selected, I would say, leading young statisticians will present their recent works and elaborate on different aspects of this topic. We have three great speakers in the order of their presentations. Dimitri Konen of, I hope to pronounce well, Université Libre de Bruxelles in Belgium. Then we will have Stanislav Mlach of Faculty of Mathematics and Physics, Charles University, Czech Republic. And finally, Paolo Mojarowski of LTCI, Telecom Paris, Institut Polytechnique de Paris, France. The webinar will be discussed and it is jointly organized with Germain van Pever of Université de Namur, Belgium. I hope to pronounce everything well, and I give the floor now to, firstly, to Dimitri. I also pronounce the webinar is recorded and live streamed on YouTube. Later, it will be accessible on the YoungStats YouTube channel. And for the questions, please insert them in the chat, and we will try to ask them during the webinar or in the follow-up debate at the end. So thank you, Dimitri. The word is yours. We don't hear you.
Sorry, I was talking alone, unmuted.
Great.
Thank you very much for inviting me and for the introduction. Do you see my slides?
Not on full screen. We see them, but maybe put them full screen.
Now should be better.
Yes, yes, great.
Okay, so good afternoon, everyone. I'm glad there are so many of you and giving the first talk in front of such a broad audience. In this presentation, I will talk about spatial ranks of probability measures over Rn, which are multivariate analogs of the univariate CDF, and the possibility to recover the probability measure from the spatial rank only. The outline of the talk will be as follows. I will first recall some basic facts about spatial ranks. Then I will state the main question I'll be addressing in this talk and present you how this problem can be solved. And finally, I will discuss some perspectives related to this work. So let me start by recalling basic facts. For the sake of convenience, let me denote P of X, the set of probability measure over any measurable space X, and then consider a probability measure over R and Z, a random variable following the distribution P. And then the usual univariate CDF of P is just, well, the CDF I presume you all already know. And then let me argue that the following quantity, which I call center outward CDF, is more natural to consider than the usual CDF. And the reason for considering this instead of the CDF is that recall that quantiles are defined as inverse images of the CDF. So the quantile of order alpha is the inverse image under f of alpha. And then with this new center outward CDF, the most extreme quantiles 2 plus infinity are associated to an alpha close to 1, while quantiles, the most extreme quantiles on close to minus infinity are associated with an alpha close to -1. And the median, instead of taking alpha equals 1/2, is obtained by taking alpha equals 0. So the reason why this is more natural is that this is more compatible with the left-right symmetry of R. But essentially, it is the same as the CDF. It is in smooth, even linear bijection with the CDF. It's the same object, just shifted a bit. And then now I can just rewrite the center outward CDF as follows. Just rewriting exercise. And then you can express the center outward CDF as just the sign, the expectation of the sign between point X and the random variable Z. And then this just naturally gives rise to a multivariate extension by just taking the sign in a multivariate sense, recalling that the sign of a number in R is just the number itself divided by its absolute value. So we do the same in Rn. We just take the vector itself divided by its norm, and it's a sign, and it's a map with values in the unit ball instead of the unit interval. So this is basically the definition of a spatial rank of any probability measure over RD.
Dimitri, there's some noise. Dimitri, do we hear each other?
Yes, we do.
There is some noise in the back. Maybe just to let you know, I'm not sure, but something is
going on.
Yeah, but please continue. Please continue.
Okay. Do you hear me well?
Yes.
Okay.
I think you're brushing your mic at some point. I don't know exactly where the mic is, but you're touching it.
I'm touching my. Okay, I won't touch anything. So I was saying, computing the spatial rank RP of a probability measure P is actually easy. The relation, the formula is explicit, and you can compute the spatial rank analytically or numerically really easily. It's just computing an expectation. Now, the question is, knowing the spatial rank only, can I recover P from RP? And there is a first result in this spirit given by Koczyński, which states that the spatial rank RP fully characterizes the probability measure, namely if the spatial ranks associated to two different probability measures are equal, if they coincide over the whole space RD, then the probability measures also coincide. Okay, that's a result, but that's encouraging, at least, but it's quite abstract. This result is theoretic and gives no insight on whether it is possible to recover P in practice. And this question was also raised for other concepts of quantiles and depth. For instance, it was showed that half-space depth does not characterize the underlying probability measure in general, but it does so within very large classes of probability measure. You can see, for instance, the papers of Stanislav of 2019 and 2020 on the subject. The center outward ranks and quantiles based on optimal transportation also characterize the probability measure. And actually, the recovery of the probability measure is explicit from the rank because they are linked by an explicit PD. This PD is quite complicated. It's a highly nonlinear PD, but still it is. So this is an interesting question, and I addressed this question for spatial ranks. Now, let me adopt the terminology of inverse problems. So we have a forward operator, which to any probability measure associates its spatial rank, or P. Can we recover the backward operator? So this is the problem. We don't even know if such a backward operator exists. Inverse problems are very complicated in general, and recovery is not always possible nor granted. So the crucial fact to notice for solving this problem is to observe that the forward operator is a convolution. So the spatial rank is a convolution between a fixed kernel, K, and the density, say, but the probability measure in general. So it's a convolution between K and the density, say. But treating this object when P admits no density is much more complicated because it's a convolution between two abstract objects, and it must be treated via distribution theory. Distribution theory here in the sense of generalized functions, not a distribution as probability distributions. So it's complicated, but okay. It's a convolution. Convolution are well understood, and when one sees convolutions, we all should have instincts, and we should all want to take a Fourier transform. So the heuristic is just simple. We want to take Fourier transform on both sides, and the Fourier transforms the convolution into the products of between the Fourier transforms. So the heuristics is as follows. In theory, we should just isolate the Fourier transform of P, or the density Fp, by dividing in some way by the Fourier transform of K, and then taking the inverse Fourier transform to recover the density, or P in general. But doing this requires two things, which are not easy dealt with. First, we should compute the Fourier transform of K. This is not easy. I did it, but it's not easy at all to do it properly, I mean, because K is not an integrable function, not even an L2 function. So this truly requires distribution theory. And then one cannot just simply divide by the Fourier transform of K, because K and its Fourier transform are vectors. So you cannot divide by it. But somehow we could manage to do that and recover Fp. And actually, we ended up with a very general result. So the answer to the question is the following. Any probability measure that is without any assumption on P, any probability measure can be recovered by its spatial rank, Rp, by the following linear PDE. It involves a constant, gamma d, which is given in closed form, minus delta, which is just the Laplacian, and nabla dot, which is just the divergence operator. And this equality always holds in the sense of distributions. So even if Rp does not possess enough regularity to take derivatives, this equality still makes sense in the sense of distributions. And when the rank Rp has enough regularity to take derivatives, and P admits a density, this equality is just a pointwise equality on the right with true derivatives of Rp, and on the left, you just replace P by its density, and it's a pointwise equality under assumptions, but essentially under minimal and optimal assumptions, which I do not detail here because it's not relevant. So in general, this equality holds in the sense of distributions, and what this means is just the last integral you see at the bottom of the slide. So this is, you just take integrals against every nice function, and nice functions here is functions from the Schwartz class. So with infinitely, so smooth, with rapid decay at infinity. But that's not very important. So now, if we take a closer look at this PDE, you might see that we take the Laplacian to a certain power, d minus 1 over 2. And it is not always an integer. When the dimension d is odd, this is an integer, and it's just the usual Laplacian operator taken d minus 1 over 2 times and applied to divergence of Rp. So there's no problem in odd dimension. But when d is even, d minus 1 over 2 is not an integer, it's a fraction. So the operator minus Laplacian to the power d minus 1 over 2 is actually a pseudo-differential operator. It's a fractional operator. And well, how do we define it? It is defined spectrally by taking Fourier transform. So taking the Laplacian in the Fourier space just corresponds to multiplying the Fourier transform of the function you're considering by the squared norm. Taking the Laplacian L times just corresponds to multiplying the Fourier transform by the squared norm to the power L. So now the generalization for an arbitrary fractional power of the Laplacian is straightforward. The S power of the Laplacian is just multiplying the Fourier transform by the square norm to the power S. So this is quite straight, and it also makes sense in the sense of distributions. That's why I didn't say anything on the assumed regularity on U. Well, and we have a power d minus 1 over 2 in our PDE, for example, 1.5. And when you have a power 1.5, let's say, it just corresponds to taking the usual Laplacian operator an integral number of times for the integer part of S, and then for the remaining fractional part of S, so 0.5, if d minus 1 over 2 is 1.5, you just have this Laplacian. So in general, it's enough to just assume that S is between 0 and 1, because the rest just corresponds to usual differential operators. So just now, just so you know, you understand all quantities involved in this PDE. So there is a problem with these fractional operator. These operators are not local. In what sense? In the sense that usual differential operators are local. they are of a local nature in the sense that their value at some point x does only depend on the values of the function in a neighborhood of x. So this is why we call them local. On the contrary, fractional Laplacians are non-local. So the value of a fractional Laplacian of a function at a point x depends on all values of the function over the whole space. And this can be seen from the following representation formula. So this is an alternative representation of fractional Laplacians. Doesn't matter where it comes from, but with this formula, you see the dependence of the fractional Laplacian on the whole domain, because it involves the integral of u of z over the whole space. So it is non-local. So it has consequences, actually severe consequences. In odd dimension, the fractional Laplacian, and therefore the PDE, is local. So we are able to refine the result from Kolczynski. If two measures, if you are given two measures over RD, and if their spatial ranks coincide not over the whole space, but over an arbitrary open subset of RD, then the probability measure coincide over this open subsets. And that's another manifestation of the local nature of the PDE in odd dimension. However, since fractional Laplacians are involved in even dimensions, this is not possible. So you're stuck with the result from Kolczynski, and no local result can hold in general. So this is pretty serious an issue, I'd say. This duality between odd and even dimensions, but well, it's life. Okay, let me now discuss more nice features of spatial ranks that I could deal with thanks to the PDE I established. So let me talk about weak convergence of probability measures. In R, the CDF characterizes weak convergence in the following sense that you all know. Probability measures converge in law if and only if the CDF converges pointwise at any continuity point of the limiting probability measure. Actually, yes, and of course, when when the limit distribution is non-atomic, this convergence is not only pointwise but uniform over the whole space. Actually, the PDE I established allowed for a similar result for spatial ranks, and actually it's the same result. Spatial ranks characterize probability measure convergence in low, weak convergence of probability distributions in exactly the same way the univariate CDF does. So convergence in low happens if and only if spatial ranks converge pointwise, except at atomicity point of the limit distribution. And in this case, if P is non-atomic, the convergence is also uniform. And proving the Glivonko-Cantelli result, so the uniform convergence, has nothing to do with the PDE. It's an independent result. But proving that spatial ranks characterize convergence in distribution required explicitly an intensive use of the PDE, linking a probability measure and its spatial rank. So it was not known before that. So as a final remark, so let us combine these two results for spatial ranks, convergence in weak convergence and Glivonko-Cantelli result, combining them to see what's happening. In R, in dimension 1, the fact that the CDF metrizes weak convergence together with the Glivonko-Cantelli result gives rise to the Kolmogorov distance on probability measures over R. Namely, just take the supremum of the difference of the CDFs between two probability measures. And this distance metrizes weak convergence. And it's almost an if and only if, except for atomic probability measures. But essentially, it metrizes weak convergence. So it's natural to look for a new distance on probability measures over RD for arbitrary D by considering the supremum of the difference between their spatial ranks. And in the same way as for Kolmogorov's distance, it metrizes weak convergence, and it's almost an if and only if. And so this is an extension of Kolmogorov's distance, and which metrizes convergence in law. And actually, it is weaker. It is weaker than the very popular Wasserstein distance, because Wasserstein distance, in addition to weak convergence, requires convergence of some moment of the distribution, which we do not for the spatial rank distance. So that's a potentially very interesting metric, which has a great advantage, is that it is given in closed form. It's just the difference between two expectations, while Wasserstein distances can be very, very difficult to assess and compute, even numerically. So this is a given in closed form and could lead to new ways of bounding distance between probability measures. But this is quite a hard task, and giving quantitative bounds on this distance, it's quite a hard task. I've not been able to manage it for now. So if any of you are interested in in working on it with me, I'd be happy to receive an email if you have many great ideas for doing this, because I'm pretty stuck on this problem at the moment. And that will be it for my talk. And I hope you will enjoy the next talks.
Thank you a lot. Virtual clap, naturally. Great presentation. Are there any questions? Quick questions from the audience? I just ask one quick one. In the derivation, you used a kernel at the start, and I think in spatial problems, there are a lot of interesting kernels like Matern kernels and similar. How about here? Are there any options possible in terms of the selection of kernel?
To change the kernel, you mean?
Maybe, yeah, to a different one, or
it could be, but you would end up with something different than spatial rank. Actually, here I wrote K to just mention that it's a kernel, but the kernel is fixed in the spatial rank problem. And actually, I've thought of it like changing the kernel and see what concept would come from changing the kernel. And actually, I'm not sure it's such a good idea, because you would definitely end up with new concepts with different features. But in the end, the approach you have to use is still a Fourier transform approach, and the kernel might have better or not nicer properties. And in the end, you might still end up with a fractional linear PDE, which displays this duality between odd and even dimension. So it strongly depends on the kernel, and there are no guarantees that it will give something more interesting in general. So you would have to choose the kernel very carefully.
Okay, great. Thank you. Thanks. Thanks again. I suggest we move forward. Now there will be discussion also later. So Stanislaw, please also share your slides. Thanks again, Dimitri.
Yes. Can you see it properly?
Yes.
Perfect. So thank you very much for the introduction. Thank you very much for inviting me. I would like to talk about the half space depth, which is kind of perhaps a bit more classical depth in multivariate statistics. And my talk is going to be much more elementary than Dimitri's, so I believe that it's going to be much simpler to follow. I would like to point to certain connections between statistical depth and particularly this half space depth with certain notions from convexity theory, from convex geometry, which are called floating bodies. I will get to that. So first of all, what is the half space depth? We already heard something about the depth, so let me just introduce it very briefly. For me, this curly P RD will be just a set of all Borel probability measures on RD. And a depth, formally speaking, is any mapping D, which to a point X in RD and a given probability measure P in this PRD, assigns a number between 0 and 1, which is the depth of the point X with respect to the distribution P, which should mean that the deeper the point X is with respect to the geometry of the distribution P, the higher the depth value should be, the higher this number should be. And what it means is that these points should be considered something like central points with respect to this given measure. Let me consider these two bivariate examples of usual just random samples here, which are of course empirical measures if you want. And if I want to compute the depth with respect to these empirical measures, what I obtain are that these orange points in the center of the cloud are the 10% of points which have the highest values of the depth with respect to this random sample. Somewhere in between them, in the middle, will be a single point whose depth is the highest, and that will be an analog of the median to this bivariate data, if you want, depth median. And as I move from the median in any direction along the line, I would expect that depth will not increase or decrease, if you want, until I reach these green points, and they are the 10% of the points with the lowest values of the depth with respect to these two random samples. So that in a way, a depth should introduce a kind of a concept of ordering, but not ordering from the left to the right as we have in real line. In multivariate spaces, we will have to order, let's say, from the most central points, from the depth median to the most outlying points, if you want, to the points with the lowest depth value. So how to compute the depth? There are very many depths. We heard already about the spatial depth. I would like to talk about the classical half space depth, which is due to Tukey from 1970s, where Tukey proposed that the depth could be computed as the infimum, the smallest probability of a half space H, such that the half space H contains my given point X on its boundary. So what do I get is exactly this. This is just a toy example. I have 10 points, empirical distribution on these 10 points in dimension 2. And I would like to compute the depth of this orange triangle here in a plane. So what I need to do, I need to go through all half spaces whose boundary contains this orange point. These are half planes whose boundary line contains the point. And I have to evaluate the probability mass of all these half planes. So this is one half plane. It contains 4 points out of 10. That's probability mass 0.4. There's another one which contains 5 out of 10. And there is another one with only 3 points. And it's very easy to see that there is no other half plane whose boundary passes through the orange point and contains less point than 3. So therefore, I will declare that the half space depth of this point with respect to this random sample is 0.3. Very easy so far. How to use the depth? It's very useful because basically what you can do is that you can generalize multivariate ranks, quantiles, or orderings to multivariate case. Just you have to rank according to the centrality with respect to the distribution, not from the left to the right. And just as a very single application of the half space depth, I chose the famous back plot, which is here on the right-hand side, which is essentially a box plot for bivariate data. Because what you do for univariate data, as you have on the left-hand side, essentially what you do, you find the median. You already have a median also in the multivariate case. That's the half space median, the depth point that maximizes the depth. Then you have a box, which is essentially 50% of the most central points, if you want, in your univariate setting. The analog of a box will be, let's say, the convex hull of the 50% of points in a data set with the highest depth values. That's called the back in the bivariate case. And then you just inflate the back and you can detect observations which may be potentially outlying. So this is a very famous concept, quite a lot used in practice, and it's based on the half space depth. It's really just a single application. There are many more. But I don't really want to talk about the applications of the half space depth. I would like to talk more about the theory and these connections to geometry. And what's very interesting to see that it's very easy to write down the upper level set of the depth function. Because for a given probability distribution P, the depth level set at level delta, which will be denoted by P delta, it's just defined as the upper level set of the depth, meaning the set of all points X in RD whose depth is at least delta. And that could be written in a curious way, which is very useful. It could be written as an intersection of all half spaces. These are just arbitrary half spaces whose probability is at least 1 minus delta. So what we see from this, it's very simple. Second, because it's an intersection of half spaces. Half spaces are convex sets. Naturally, this thing here, P delta, has to be convex. And we can write it very nicely because this formula is actually very simple. So it has to be a convex set in any dimensional space. And what can I do? I can take just a simplest non-trivial example I could think of in dimension 2. I could just take the uniform distribution, a square. And what do I get for this uniform distribution? Here in these half spaces, the probability of a half space is essentially just the volume of a half space, because then the probability is proportional to the volume. So I'm just taking the intersection of all half spaces or half planes, if you want, whose volume, when intersected with the square, is at least 1 minus delta. And this is indeed a very simple construction. It's not very surprising that this occurred also in geometry very long time ago. And that's what I want to talk about. So we come here in history. It appears that, as far as I know, the earliest mention of these concepts in geometry comes from 1822 from Charles Dupin, who considered the concept of so-called floating body. Just really compare this with the definition of the Tukey's half space depth, which was a statistics proposed in the 1970s. Completely independently of that, in geometry, people have been considering actually equivalent concepts. I want to get to that. And what are these equivalent concepts? They are called floating bodies. This is just an illustration from the original book of Charles Dupin from 1822. What Dupin defined? He considered not general probability measures, but only, if I want to phrase it in our terminology, only uniform distributions on convex sets, which they identified with the convex sets themselves. So he had a convex set K in a d-dimensional space. He had a constant delta, which was small enough. And he said that a convex body, that is a convex set with non-empty interior, K delta, which is a subset of K, is the so-called Dupin floating body, or just a floating body, if it has a special property that each supporting hyperplane of K delta cuts off a set of exactly volume delta from K. So what I have here essentially, I have a big body K, and I have a smaller subbody, which will be my K delta, and it's a floating body if and only if each supporting hyperplane cuts off from the bigger body a set of volume K, volume delta. So what led Dupin to define this concept? And because it's called floating body, of course, has to do with flotation of let's say, solids in water. And just for an illustration, let's take some egg like this, which will be now a convex body in dimension 2. And let's suppose that this is really a solid, let's say in dimension 2, of volumetric mass density 0.3. What I do with this solid, I place it onto the water surface. The water surface is this blue line, and I will let the body submerge into the water until it begins to float. I do not allow the body to tilt to the left or to the right. I just submerge it in direction perpendicular to the water surface until it begins to float. According to the Archimedean principle, it has to float when the volume of the body submerged in the water is exactly proportional to 30% of the volume of the whole body. So 30% is below water, 70% is above. Now I will do it from some other side. I will rotate the body a bit, and I will again place it onto water, and I will let it submerge until it begins to float. I again make a mark where I had this water surface. And I will just do the same from each direction. So basically, I just rotate my convex body on the water surface, and I consider the part of the body which, no matter in which direction I put it onto water surface, remains afloat, which remains dry. That's the part here which is inside this one delimited by this red boundary. And this is actually exactly the floating body of Dupin. So this was the original motivation. Dupin wanted to study how do convex solids float in water. It's very easy to see that if I take a particular case of the convex body K in a d-dimensional space and I identify it with a uniform probability distribution on this convex body, then if this Dupin floating body exists for some level delta, then it has to be exactly the upper level set of the depth with respect to the uniform distribution on this body, also at level delta. And what's quite curious is that we observed these connections. We contacted people from geometry who have been working on these problems for many years, and they were very surprised because they never really saw the concept of the half space, that they never heard about it. And it appears that truly, this has not been recognized in neither of these fields for many years. And what we were able to do, I contacted some very prominent researchers in the research on floating bodies, Carsten Schüder, Elisabeth Berner, and together we wrote an extensive survey paper where we really gathered all the theory from both fields, and we really emphasized the links, and we obtained a lot of interesting results. So I want to talk about particular result, which is actually very closely connected to what Dimitri was talking about, except that I will not be interested in spatial depth, but I will be interested in a problem of characterization of measures by the half space depth. Dimitri mentioned this. And the question goes as follows. That for any two different distributions, P and Q in RD, exists a point, some point, such that the depth of these two distributions are different. A possible positive answer would be exactly what Dimitri was working on. That would allow us to essentially find one-to-one link between all probability distributions and all half-space depth functions. That would justify a full-blown non-parametric inference of measures using the half-space depth, because you could use equally well either the distribution, the measure, or you could use equally well directly the half-space depth, and you could go from one to the other. So people have believed for a long time that this is true, that there cannot be two different distributions with this property. And there were a lot of partial positive results towards this so-called characterization conjecture. So partial positive results have been available for dimension 1, where the depth could be written just directly in terms of the distribution function. Of course, distribution functions characterize distribution, everything is fine. It was also known that if P is a purely atomic measure with finitely many atoms, then the depth characterizes the distribution, and you can actually recover the distribution directly from the depth. And then there are many other results, and you can see that there was quite a long array of these results, and it appeared when we really approached this problem that it would be very difficult to construct a distribution where this would not be true, because you could see that if the distribution has a density, if it's integrable, apparently it's already true. One condition which I don't really want to talk about is if all floating bodies of P are smooth. That's another difficulty, but it's one of the conditions under which we can actually guarantee that there is no other distribution with the same depth. And several people already conjectured the general positive answer that you cannot have two distributions, different distributions with the same depth. When we looked into these results more carefully, we found that several of these results were problematic. Several of them were unable to recover without encountering problems in the proofs. So if I really cross out all those which we found that really the proofs are with difficulties, we in the end find that only the atomic measures, all measures which satisfy certain very curious condition on floating bodies, are indeed possible to be guaranteed to be characterized by the half-space depth. So the problem remained open again, and to answer it, we were able to use some relatively simple construction which actually originates in Fourier analysis or in convex geometry to prove the following result, that surprisingly and unfortunately, for any dimension d bigger than 1, we were able to find two different measures in the d-dimensional space with exactly the same depth. Now I actually even have a proof here, but I don't really believe that I want to go into it. I don't believe that I have that much time to go through. Maybe let me just remark that the proof is surprisingly very simple, and I was able to cram it here into something like 2 slides. And what it uses is the concept of so-called alpha-symmetric measures. The alpha-symmetric measures are simply a direct extension of spherically symmetric measures, which are in this case also 2 symmetric measures. And they are defined by means of the characteristic function, which is essentially just the Fourier transform of the distribution, in a way that a measure is called alpha-symmetric in a d-dimensional space if its characteristic function can be written as the L alpha norm, this is just the usual L alpha norm in LP spaces, of the d-dimensional vector T. And for these distributions, they have a very nice special property that you can explicitly write the distribution of all projections of such a multivariate measure X, or random variable having this multivariate measure P, into any line in direction U. And you can actually show that all these projections into each line are just multiples of the first marginal distribution of the vector x, x1. If you use this and you plug it directly into the expression for the half-space depth, you find the explicit version of the half-space depth of any point x with respect to each such an alpha-symmetric distribution. And what remains is to really show that there are 2 different alpha-symmetric distributions which give you exactly the same expression. I don't really want to go into details, but it turns out that it is true to have this. What you need to use for this to really prove that you can have 2 such alpha-symmetric distributions are some results on positive definite functions, but these results were fortunately already known in mathematical analysis, let's say from the 1930s. That was really nothing that we found, we just used them. And in the end, we were really able to find whole families of distributions with exactly the same half-space depth. So here is just one example. I take dimension 2, and I take 2 different parameters, alpha 1 and 1/2. Here I have two distributions and the densities. The densities are impossible to be written in explicit form, but you can calculate them numerically using the inverse Fourier transform if you want. And the level sets of the densities are these contours with these orange contours, essentially. You can see that the two densities are definitely very different. But if you really go through the construction that I provided before, if you evaluate the exact half space depth, you will find that all the half space depth level sets that are these floating bodies, if you want, they're all just rectangles centered at the origin, and they also decrease as you go from the origin in a direction at the same rate. So you really get exactly the same depth for both of these distributions. This is quite a surprising counterexample, which actually shows that probably the half space depth is not as optimal, not as great as we believed before. So just to wrap up, what do we know, what we don't know? I've shown that convex geometry and statistics are not as different fields as they seem, that there are actually tools of convex geometry which have been used in statistics, and there are overlaps. We found that the half space depth and the floating body are essentially the same concept. There is really no difference between them, and there is a lot of research on floating bodies in geometry which we were unaware of in statistics. Unfortunately, we know now that the depth, half space depth, does not characterize all the distributions, but there are still very important open questions which we don't know how to answer so far. First, the obvious one is under which conditions can we really guarantee that the half space depth characterizes the distributions? We know that it doesn't characterize always, but we believe that for large classes of distribution, it still characterizes. We don't know how to describe these classes. A beautiful example for which we don't know if there can be any other distribution with the same depth is already the uniform distribution on a triangle in dimension 2. Because for uniform distributions on other simple bodies, you can really show, using some results that we have, that the depth characterizes the distribution. For triangle, we don't know this, and it appears to be a relatively difficult problem. And the last question is, when are these floating bodies of measures, if you say smooth? This is also a highly non-trivial problem, which is very important, not only in statistics. It has definitely great importance in statistics, but also people struggle with exactly the same problem also in geometry, with some very different motivations and very different background and everything. So it appears to be a quite challenging problem, which definitely needs to be studied in the future. Here are a few references. Thank you very much.
Thank you. Thank you, Stanislav, for a great presentation. Again, virtual clap. Any question? We have some time still. Another short one from me. I'm not an expert, but does your construction hold only for half space depth, or depth functions in more general, say Tukey, autoregressive, Pareto, and others?
Half space depth is Tukey depth. It's the same. It's just called different.
Okay, yes. Yeah.
But for other depths, I don't believe so. There could be variants of half space depth which are called weighted half space depth, where instead of something like a half space, you consider, let's say, a cone, something like that, and then you just search for the smallest probability of a cone whose apex passes through some point. Maybe for something like that, but I really don't know. I never checked this. I have no idea.
Okay. So
but this construction is really very specific for the half space depth.
Okay, thank you. Thanks again. Let's move forward now to the final third presentation by Paolo Żarowski. Paolo, please. Yes, share the screen. Great.
Yes, so thanks. Thank you for this invitation. So what I would like to present is, so at the beginning of his talk, Stanislav said that his talk will be simpler than the previous one. So my talk will be even much simpler. So I will speak really about more application of the data depth, and more precisely, the application I will be speaking about is the anomaly detection, right? So I'll So I'll start by what is anomaly detection, why it's important, and then I'll present the further material, which will actually be about how to use data depths to do the anomaly detection, right? So this data is actually motivated by a real problem which I encountered in my professional activity. So it's about a production line where we produce some items, and these produced items we produce them, they pass through production stations, and we can measure their characteristics, right? And we usually measure, of course, many characteristics, and we can have many items or little items, depends how long is the production cycle, right? And here, to represent in a two-dimensional space, right, on a plane, I took only two characteristics, two measurements, right? So imagine that this is some produced item, for which we just visualize here two characteristics of this item, right? So, and now you see that here we are in the logic of machine learning, right? So we have something which is called the training sample. Training sample is these 500 black points. These are not real data due to confidential purposes. This is the simulated data from normal distribution, right? And then we have, and this is our training data, right? And we are in unsupervised framework. This means that we do not know whether which of the data inside of this training data are anomaly or not. And then we have now on the phase of work, we have 8 blue points, and for these blue points, we would like to say, for each of them, are they anomalies or not, right? So apparently, in this simple case, where we can see the data, which is not the case when dimension grows, we see that the 4 green points here are normal data, and the 4 red points are rather anomalies. Here it's super simple. I'll stick to this kind of examples to really give you an idea of how the anomaly detection works. Okay, so now let's try to formalize it from a mathematical point of view. So we can say that we have some training set, which consists of n points in a d-dimensional Euclidean space. And what we want to construct, right? What we want to construct is some decision function, g, which would take, as an example, 1 point, right? So we really don't care about the data itself. We have 1 point, one produced item, and we want to say, okay, based on measurements, is it anomaly or is it normal, right? Anomaly means we have to throw it away, we have to redo it, or normal, which means that we can sell it to the customer, right? And you would like the decision of this G would be like this, like 0, it's fine, or 1 identified event as anomaly. Okay, this is great, but we would like also to have to do a bit more, and then we would like to have not just the binary function, but why not to have something which is the entire interval, or the entire, like, say, real value, usually it's between on some other interval, but real value, which will reflect the degree of abnormality or degree of centrality, right? And this is how you start to understand after the 2 previous talks that actually can speak about data depth, right? So let's look again at our example. So now what actually people do in practice without any data depth, actually without even any statistics, well, still some. So what they do, they use bounding box. It's very actually handy tool because you, when the item is being produced, you can immediately already after first measurements, you just check for this first measurement, minimal, maximal, admissible values. If it's not in these bounds, you know that it's already a bad item. Of course, using this mechanism, we cannot detect all the anomalies. We'll detect 3 of them by chance if we are lucky, but all anomalies which are here and here we will not be able to detect due to correlation in the data. And clearly, the volume of these corners will be growing with the growing dimension, right? So at some point, we will not be actually detecting really a lot of anomalies. So this is why the clever way would be to use a Mahalanobis distance, or which can be then formulated as Mahalanobis depth in the logic which you have seen just in previous talk, which will say, okay, let's find some contour, right? And let's say that if Mahalanobis depth is smaller than some value, this means that the points are outside the contour, the points are, then the points are anomalies, right? And otherwise, inside of this circle or this ellipse of like smaller Mahalanobis distances or larger Mahalanobis depths, they are normal. And of course, we then detect all items. And in this simple setting, everything seems nice, even if here we can construct settings where it wouldn't work, right? So, but now what happens next? We don't always have so many points. We can be in this kind of situation where, for example, items are very expensive, right? We don't produce like each item for several seconds. We produce once per few months, and we have only that many of them. Or maybe we just started the production and which is not well adjusted. So actually there are anomalies. It's exactly the moment when we can expect many of them. And so in this case, what we would like to do, we would still like to detect the anomalies. But if I do something I've done just before with the Mahalanobis depths, I will get this contour. And this contour will tell me all data are normal, which is completely wrong, of course, right? So, but now if we use a data depth approach, we will get contour like this of normal data, right? And this contour will tell us that these data are normal and these are anomalies. So we will actually detect anomalies without any problem, right? So we will say everything which is outside, which has too small depth values, are anomalies. Everything which is inside, which has high enough depth values, are normal data. And even if the number of points will grow, our contour will be changing, adjusting to the geometry of the data. And finally, it will be actually closed. We'll have this robust contour, which will work from the very beginning and continue working, not worse than the Mahalanobis depths, which we had here. So now the question is, yes, how to do it in a more general framework and not just a handy example? And the answer is the data depth. So luckily, Stanislav in his talk gave a really very nice and very clear, I think, introduction to data depth. I, of course, prepared it as a backup, but now taking into account that we also have limited time, I will not stop on it, and I will immediately pass to the following stage, right, using the data depths. I'll just mention that Stanislav has presented the half space or two-key or location depths, they say its names. There are other depth notions already for multivariate data. These are some of them. Some of them which are really used. There are also more which have been, and there are even more which have been suggested. And for some reason, the articles have not been, for example, accepted. This happens. We know that. And this is in multivariate space. There is also data depth notions in functional space, in space of curves, for the space of matrices, for the space of spherical data, right? So now how to use all this to do anomaly detection. And look, let's start with a very simple example. So let's look at this example. It's the same data, exactly the same data, just two different notions of data depth. So we have 90 points generated in this way from which are normal data, and 10 points which, again, in bivariate space, obviously anomalies. Imagine if the dimension of space is higher, it becomes less obvious. Okay, so what we can do, we actually can find some certain depth levels denoted here, right? We know that all data which is normal has data depths 0.194 or higher. These are data which are here. And we will see, then we plot them, I'll show you the plot later. We will see that the anomalies will have some gap in data depths and will have much lower depths. This is for the projection depths, right? So basically, it's somehow a perfect case of how you can apply data depths to detect anomalies. Another example, we take another depth, it's simplicial volume depths. It works in exactly the same manner as projection depths, but what I wanted to attract your attention here is that the simplicial volume depths actually is applied here, and it's not a fine invariant version. This means that if it is not doesn't keep the value if we transform data using linear operator. And you see that the contours look a bit weird. They do not completely fit the data. And you can imagine if the depth would be a fine invariant, like projection depth, the result would be better. Okay. So this is a nice case. Now in reality, cases are a bit worse. And what we have, I took now exactly the same distribution, but I added 25 masking anomalies, right? So there are some noisy anomalies added here in the circle, right here. So basically projection depths. And now I took also half space depths, another depth notion. So also the one about which Stanislav was speaking. So in the previous talk. So what we can see actually with projection depth, again, we are able to detect all anomalies, both anomalies which are disturbing, but also the group of anomalies which are here. The same is a bit true for half space depth. We also can detect these anomalies, and we can somewhere see the normal data. So basically, we will be able to detect majority of them. So now, okay, it's true that we rather look at the at these points here. We see it, but what is the picture? Because this we cannot see if dimension is 3 or higher. 3 maybe still, 4 we already need to look at projections. Higher dimensions, there are too many projections, we can't look at. So basically, what we will see will be the picture like this. And this is where it's important, whereas the data depth actually can bring some insights. So for example, for projection depths, in this example, you will see the following picture. And now imagine you do not see any color or difference in points, right? I just added them because we know where the anomalies. So even if these points all would be just blue dots, you would still be able to understand that something is going on here in the data. And even if you don't see it, how it is the case for the half space depths, you still, so you don't know where the anomalies start, but you still would be able maybe to choose some reasonable threshold, maybe speaking with the experts of some application domain, and they would suggest you some thresholds. You would have some mistake maybe, but you would have detected the majority of anomalies, because actually due to half-space depths, in this case, anomalies are rather in the tail of this distribution. They are rather taking low values.
Paolo, may I
Yes.
just shortly interrupt? Just one short question in the chat
Yes.
related to what you're speaking right now. Is there, Imad A. Shah asks, is there any similarity between the local outlier factor, LOF, and the depth-based approach for detecting anomalies?
Absolutely, it's even more. It's the next, the after next slide of what I'm going to present. I will present them
Okay.
both. Yes,
Thanks.
I will speak
Thank
about
you.
local outlier factor.
Great. Thank you. Thanks.
Thanks for the question. So now I would like to speak about the properties. So maybe here the disclaimer I will repeat at the end. I will put a disclaimer. So I'm not trying in this talk to say that data depth is a panacea to detect anomalies. But what I try to say is that there are cases where data depth is the best thing to do, or is a candidate for the best thing to do if you have the anomaly detection problems. But there are, of course, situations where it's not the best solution. Okay, so let's be clear on that. I'll repeat it as a disclaimer at the end during conclusion. So we will now speak about properties in a more harsh situations, now closer to reality, where we are in difficult situations where we might not see the data, or the data is more tricky. And we will speak about three properties of data depths which are actually better than in the machine learning methods you might know. We will compare data depths with autoencoder to reflect the robustness of data depths, about its extrapolation abilities, that is ability to predict where we did not have anything. It's using the comparison with local outlier factor, one cluster protector machine isolation forest. And we will speak about explainability of data depths in the case of anomaly detection. So first of all, autoencoder. I will not go in depth what is autoencoder. It's a neural network based tool to detect anomalies, and it's actually very widely used in practice. Okay, so but there are certain properties of autoencoder which actually impede two things at the same time. It's robustness, because it has loss, which needs to have certain degree of smoothness or continuity to be able to train the neural network in the stochastic gradient descent method. And another thing is explainability, because neural networks are known to be intrinsically unexplainable, even if currently, since several years, there is a path of pioneering works to try to inject explainability in the neural networks literature. So what we do here, we have normal data and we have some basically extreme deviations, which are anomalies, right? So there is 1,950 normal data, there is 1,000 data points, and then some percentage of them will be put anomalies from Cauchy distribution. So what you see here, okay, so what do? I compute the score of normality, abnormality, whatever you call it, which orders the points using the machine. Machines, there are three machines. There is data depths, there is neural network autoencoder with L2 loss, and autoencoder with L1 loss, which is supposed to be robust, but actually it's not, for the same reasons as L2 loss. So, so what I do, I order the points by their score, and then I put the threshold to detect all anomalies. Okay, so that I correctly attack all anomalies. All anomalies are correctly defined. But then what is of course happening? If my tool is good, I will have only anomalies. If my tool is not good, I will have many non-anomalies detected. And if my tool is really worse, I will have, like, you know, all the sample, right, detected as anomalies. And so what you see here on the ordinate is the portion of correctly detected anomalies, right? So if I detect only anomalies, it will be 100%. If I detect very little anomalies, it will be the portion which will be corresponding to the portion of the normal observations. So I do this in 2 dimensions, 10 and 20, and I do it. I repeat it 50 times, and I show you box plots. So, and it's actually one of the examples where data depth is indeed much better than neural network, because you can see the data depth, this is blue, yes, it actually tackles the task without any problems, like really. Okay, there are some maybe things with 45%, like almost half of the sample are. So yes, so this is a portion of anomalies in the training data. If we have a lot of anomalies, maybe sometimes we do detect, we have some false positives, what is called, right? But really not that many. But in general, you can see that like when autoencoder, it really fails, right? We still, so it detects, you can imagine, from 20 to 100% of the sample as anomalies, right? With both losses, right? The neural network actually fails, but the data depth actually does detect anomalies correctly. So now after autoencoder, and in addition, think about it that I'll show explainability for data depths, while autoencoder cannot provide you any explainability. Although you can, of course, try to look at the latent space, whereas the encoder and decoder are joined, of course. This is what actually people try to do. So now let's compare with three main machine learning methods being used. It's the local outlier factor, this one-class support vector machine, and the isolation forest. So for local outlier factor, to be honest, in dimension 2 as a neighbor-based method, and I wanted to visualize, right? I mean, you cannot really beat it in dimension 2 because once you have chosen the number of neighbors well, in dimension 2, like local methods work, right? Their problem is the cures of dimension. But okay, so just to explain you the experiment. So you see many colors. So first there is training data, and then there is test data, and there is the anomaly score. So training data consists of normal data being small blue, dark blue dots, and red pluses, which are anomalies. Okay, so the blue dots and the pluses are anomalies. And then we had test data. We put test data where there was normal data. We put test data where there was anomalies, and we put test data in the place where there are no anomalies, right? So because if it's anomalies of new kind, we have new problem we also want to detect. So basically, and then in the color you see the score which should classify anomalies, but in the color it's not really well seen. So what I will do, I will put all the observations on the line, and then the score will be here, and then we'll see whether we can distinguish them with a score or not, right? So there is first training data and test data. We have the normal observations, anomalies, normal observations, anomalies. So local outlier factor actually does work. You can believe me on word. It will not work when dimension grows because it suffers apparently from cures of dimensionality. Plus, you don't know how to choose the number of nearest neighbors. But in low dimensions, it works if you have enough data, and it can be the case because we live in the world of big data. So what is actually, even in this case, it does something actually wrong. It is that these are the anomalies. These are the anomalies which are here where anomalies were, and these are the anomalies where there were no anomalies, the new ones. So, and actually it does distinguish two groups. It gives them different anomaly score, but this is intrinsically wrong because these anomalies are as bad as these anomalies because the training sample was on its own contaminated, right? So this red pluses also should not be there, right? But otherwise, local outlier factor works. It detects anomalies. It just will not work if the dimension grows. So now let's look at the one-class support vector machine. So here it's a bit worse, but this is because this is a tool which is rather dedicated for support estimation, right? This is where it's the main of application. But so it also doesn't work well. Here it's a bit vice versa. It actually has some success in detecting the anomalies which are new because it's outside the initial support of the points, and it rather struggles to detect the new anomalies. You see, the old anomalies, where there were anomalies, because you see their score is mixed with the score of normal data. If you look at the isolation forest, well, the isolation forest actually has two problems. It has extrapolation problems in general, and it has another problem. It's these traces because it doesn't take into account correlation in the same way as other methods. It takes variable per variable when it does its splits, and it has this traces, but also you see that this trace is a bit darker because here there was data, right? So basically in this particular example, it completely fails, but it would have failed even if it would not be coinciding with coordinates. Although one should notice that now there was just in 21, I think, published in one of IEEE, if I'm not wrong, journals, although, yeah, okay, it can be wrong, the extension is called extended isolation forest, where they took rather directions on the unit sphere instead of coordinate axis. And it actually compensates for this problem, but it doesn't compensate for the general problem of inability to extrapolate. So, and the data depths, actually, it does work. So on the color, you actually can see a bit that it's darker here or lighter here. So it actually does give different depth values for all anomalies in both training and test samples, and it doesn't distinguish neither the two groups of anomalies. So what is good? So my PhD student suggested just several months ago when looking at this plot, he said actually the scale of the color should be taken rather logarithmical. And actually it's interesting, if you put the scale in a logarithmic way, you will see the even larger difference between normal observations and anomalies. So now I'd like to speak about explainability. Let's come back to the very first example. Okay, so we are able to detect anomalies. You've seen there is this line, and we see that anomalies are far. We use the usual what is called elbow rule, that there are anomalies. Okay, so we can detect them. Now, can we say more? Can we explain something about anomalies? Using data depths, we actually can. So there is some jump in methodology because, again, due to the limited time. But the point is that when computing projection depths, we will not have only the depth of the point, we will have direction pointing towards this point. It will be direction in which the data depths will be minimized. So this direction itself will already give you constituents. You know, it's like in principal component analysis, it will give you constituents how much each dimension contributes to the abnormality of this data. Now let's look a bit deeper and look at two plots. It's directions plot and angles heat map. So if we speak about direction plot, right? So what do we do here? For each point, we take direction where the direction which points on this point and which makes it to have minimal depth on this direction, and then we project all the sample on this direction. So we have one direction per 100 our points, and in projection on all of these directions, we will have 100 points on each direction. And so these are these points, these are directions. The points are ordered by data depths, and we see the in big red dot. It's a bit superposes, but we don't care. The point itself for which the depth was computed. So what we can see, we can visually persuade ourselves, we can really be convinced now that the abnormal observations are really abnormal. So we see in the projections of directions, they are on certain distance, and these 10 observations are on the same distance, right? So now what we take from this plot, that the 10 points which have the smallest value in projections on the depth minimizing directions, they will have approximately the same distance, and they are far. So they are for sure anomalies, and they have the same distance. Now we do the second thing. We look at the angles heat map. This is the angles, actually the scalar products on the scale from -1 to 1. You can see it here between each two projections, each pair of projections among these 100 projections, which look at the points when minimizing their depths. And what we can see is that, again, ordered in the depths, the increasing depth order for the points. What we can see is that the 10 directions, which of the points who had minimal depths here, they had very high values of the scalar product, which means that they look in the same direction. So what does these two plots say us about these anomalies? They tell us that they are on the same distance and in the same directions, which means that they are a group of anomalies, right? So we can even say, okay, and you understand these plots, they look like that independent of dimension of the data, right? We don't see the data because data is high dimensional, we cannot visualize them, but we can always build these plots. So after all this, one of the questions where the data depth is really, it's important for you to solve this question is the computational tractability of data depths. So let's take a look how the time will be measured in the number of directions which we need to approximate the data depths, how it develops, how the capacity of detecting anomalies develops with these directions. Okay, the main message here will be the following. Actually, I will start with this. It's that we might, instead of calculating the depths exactly, which can cause often exponential time growth, we might approximate data depths using a random, small number of directions, sometimes very small, as we see here. But this precision, which is with some error, which is approximate, can be enough to solve some particular application task. In our case, to detect anomalies. So what I do here, I have 5% of anomalies in the data, right? Which are generated in this way. I will not go into details. And so what do? I use two algorithms: the completely random search and for which, by the way, with Statistical we have theoretical results, and the refined random search, which is more guided algorithm. And what we can see is that if we, in a clever way, optimize data depths, and this method will be soon accessible in the data depths package in Python. So already for 200 directions using data depths, using like clever optimization, we can, in dimension 10, using only 200 directions, we can sometimes very well detect the majority of anomalies, and at 500 directions, which is very fast, we can detect the most of the anomalies, and even like up to 100% of them, right? And if we do usual random approximation, okay, it takes time. We would need many directions. In dimension 50, by the way, this is a difficult case here. You actually cannot theoretically detect all anomalies because since dimension grows, the distance grows, and distance between anomalies is similar to the distance between points is similar to the distance between group of anomalies and the normal data. So you can see that the one thing you can see is that using the guided search, the refined word is for guided, you can detect anomalies much better than when using just pure random search. Another thing, approximation. Okay, this is a numerical error approximation. You can also have statistical error approximation, because basically you compute depth of a sample, but what you would like to have depth of the distribution, right? But you don't know the distributions. The distribution is represented by the sample. So what is happening here? What I was trying to do in exactly the same experiment, I was just reducing the number of sample with respect to which I was calculating the depth to detect anomalies. And you can see that even in dimension 50, okay, of course, there are no miracles. If you take very small subsample of points, at some point you will detect nothing. But if you, for example, take half of points instead of all points, right, you will still detect majority of anomalies with great success, right? And if it's, for example, not a life-threatening application, it can be sufficient. Take into account that you have limited resources. And now imagine if you have more points, like 2,000, 3,000, you will be able, even with a sample, so for example, for 3,000, with a subsample of 1,000, you will be able to detect most of them. So I will just quickly conclude because my time is going out. So first of all, so data depth has been since 30 years a tool which is very attractive in its theoretical properties, even if there are still very many theoretical questions being open. And recently, in the last 10 years, maybe even less, there were really the boost of efficient algorithms, how to compute it in both exact and approximate way. So now it starts to jump from the stage of theoretical methodology to really something which can be applied in practice. And this presentation, we would like to suggest, to make a conjecture, that this can be seen as a powerful tool for anomaly detection. When applying this, the data depth for anomaly detection, one should take into account many aspects. Some of them, for sure, miss some things, are to be taken into account. And again, I'll repeat the disclaimer that the point here is not to say the data depth is in general good for detecting anomalies, but rather it's I have shown situations, and there are other ones, where data depth is very advantageous to detect anomalies. Thank you for your attention, and we'll be happy to hear your questions.
Thank you. Again, thanks for an excellent presentation. As there are no questions in the chat, I suggest we just move forward to the discussion, and there will be surely questions also for you, Paolo, at the end, then later, if you agree. Thank you again. So thanks, Germain. Please, Germain van Bever.
Yes.
Discussion.
Let me just find my slides. There we go.
Great.
And I will just put them full screen. Okay, so I think you can see my slides.
Yes.
Not muted. Okay, so well, first I would like to thank Dimitri, Stanislas, and Pavlo for accepting my invitation today. So what I'd like to do in this discussion is actually take a step back and try to think about more general questions about depth. And in order to segue into that, I first want to just briefly summarize what we've seen from these three talks, right? And they share a few common things. And so the first talk was mainly about a characterization result for spatial depth. And what you've seen in that talk is that usually when looking at the theoretical properties of depth, the mathematical treatment can be actually quite involved, right? So we've seen what happens with spatial depth. We've seen what happened with half space depth. And so Stanislas showed us some really interesting links to convex geometry and to floating bodies. And what we saw in Stanislas' talk is that it's actually complicated, and all the more so that even we sometimes make mistakes in the sense that we think that some result might hold, and in the end, they're not really true. And then Pavlo showed us a more modern version of depth, although depth is not so old, with new, very interesting visualization tools. Starting to do some comparison with machine learning, which has not been done too much up till now, and so discussed more about the computational aspects of depth, right? And they cover a good panel, a good variety of things that are characteristic of depth. So with depth notions in general, so there are theoretical challenges as well as computational challenges. So that's one thing. And you've been hopefully convinced throughout the talks that there's no universal notion of depth. And there are parametric ones, so Mananobi's depth is one example. There are non-parametric ones, mostly based on geometry, such as the half space or the spatial depth. And what's convincing throughout also is that usually the notion of depth has to be chosen according to the problem that you want to tackle. And then the last interesting question is, of course, the characterization question, right? So is a particular depth enough to characterize fully the distribution? And so my first discussion point that I would like all three speakers to consider more in a philosophical way is, well, where are the next challenges in the depth field, right? So are we going more towards computational issues, or are we staying in the theoretical fields, and are there still a lot of things to be done there? For example, so one very famous paper in depth is due to Zugo and Surfling, who proposed back in 2000 broad definitions of depth. So example of abstract depth that would cover some particular examples. And so do you think there is interest in unifying some concepts of depth in order to derive some characterization results or unify computations, right? So there are already some paths explored there using the projection depth, for example. And so what would be the next computational developments is also a natural question. Okay, so that's my first discussion point. Where do you see the field going in the future? A second discussion point, which was also somehow introduced by Bob Surfling in 2000, is the universality of depth, in the sense that it somehow characterizes interesting aspects of the distribution. And so he introduced something called the outlyingness, depth, quantiles, and ranks paradigm, where it basically states that all these quantities are equivalent. So an outlyingness measure associates roughly with any point a measure of how outlying that point is in a distribution, right? So exactly the opposite of centrality. So the higher that number, the more outlying this point is with respect to distribution P. Whereas depth is exactly the other way around. The higher it is, the more central the point is. Similarly, we have quantiles and ranks. So a quantile function associates to a given direction a quantile in that direction. Okay, so that would be a point in RP, which would be somehow associated with a direction on the sphere, on the ball, on the unit ball. And so basically, the point associated with the center of the ball would be the center of the distribution, and then the closer you get to the boundary of the ball, then the quantile would be going further and further away from the center. And ranks work the other way around. For any point in RP, you basically want to associate a point in the sphere, which will characterize how far away from the center that point is in the distribution. And what basically Surfling says here is that all these four quantities are equivalent. You can always build a depth out of an outlyingness measure. Just take 1 minus that outlyingness, for example. An outlyingness measure can also be obtained by taking the norm of the rank, for example. Dimitri showed us that the rank is the inverse function of the quantile, etc., etc. And so my question here is, seeing the very diverse definitions that we saw, should we still consider all these definitions are equivalent? Is there some interest in looking at the ranks rather than the depth? Are they always equivalent, or will we sometimes have more information in something else? So those are already two discussion points. And then while preparing when seeing those talks, so there are two aspects of depth that I think are important and that I would like to discuss, and then I have more precise questions for each speaker. So first, round of questions is about the locality of depth. And so in Dimitri's talk, there's a very surprising result about the behavior of the transformation from the ranks to the probability measure, which depends on the parity, basically, of the space, the dimension of the space. And so, I mean, of course, it's very complicated there, but so is there some intuition why this is so, why the fractional Laplacian works this way? So when we have a fractional Laplacian, it involves the whole space. And maybe a more specific question would be, did you construct an example where you can actually see that it's non-local, right? So are there a distribution where an influence somewhere impacts the probability measure somewhere else? Okay. For Stanislav, and because there seems to be still some mysteries about those floating bodies, right? So, for example, characterizing when the floating bodies are smooth. So, are there results? And I'm not familiar with convex geometry about the locality of those floating bodies. So, do we extract some local informations from them, or do we need to know the full distribution to actually be able to construct them? And then for Pavlo here, a more philosophical question, and that is, are anomalies actually something that are locally defined, right? So usually we think of anomalies as points that are in a region where, for example, the density is small, right? And so in my mind, anomalies are local behaviors that we want to detect. But the depth function is actually a global tool, right? And so is it always appropriate to use a depth function to detect local anomalies? So that would be one question that I would like you to give some thoughts about. And then finally, if I can move to the last slide, there we go. I would like to discuss a bit about robustness. Okay, so depth is known as a robust tool, and usually depth is always in those robust sections of conferences. But do you agree with this in general? Right. So we know that there are sometimes sensitive to some outliers, especially the parametric ones. And so more typical questions would be, so for Dimitri, what spatial depth is highly robust and in close connection with quantiles? So do you think we could have other characterization results for non-robust depth, or is somehow robustness connected to the fact that we are able to give some characterizations? And then well, Stanislav, the question is also slightly linked with this. So are people in convex geometry interested in robustness somehow? Okay, so are there results about the change in some measures that they are interested in when the body does not change so much, for example? And again, for Pavlo, a more philosophical one, which I had while reading his paper, and that is, should computational aspects be impacted or impact robustness, right? So usually robust measures are more complicated to compute, but is the computation difficulty enough to actually discard some of these, or should we somehow find a trade-off between robustness and richness of the model or complexity of the computations? So would there be, I'm not sure there is, but somehow a way to decide, let the user decide about the trade-off between robustness and computation, right? So these are some questions that I would like to discuss, and of course we can debate rather than just wait for all the answers. And so maybe I can suggest to do that in order of presentation again. So Dimitri, if you want to say a few things about these, I don't know if I leave my slides on or if I kill them.
Maybe, yeah, maybe you lose them, or maybe leave them, please. probably the respondents will. Yeah,
Maybe it's easier to read
speakers.
them
Yeah,
there, and then I
please.
can move from one slide to the other.
Please, please. Dimitri, I think.
Yeah, he just froze.
Just a second. Dimitri, are you with us? Dimitri?
He's frozen now. So maybe we can.
Just a second. Yeah, maybe Stanislav, please.
Yeah, exactly.
Yeah. So these are excellent questions, German, and I think that's the most important question about the debt was already asked. You gave the question, and I would just rephrase it probably that I would ask, what is a debt? What should a debt be? What do we expect from it to be? Because there are these axioms, if you want, of Zorn-Surfling, but they have been commented on, reworked in many papers. And this is still only in the finite dimensional case, only in the lower dimensional case where it's actually functioning. Surfling himself wrote you meant the paper of Zorn-Surfling from 2000. In 2006, Surfling wrote another paper where he proposed a slightly different set of axioms, which included that also the level sets of the debt should be convex. Then there were many people who argued that convexity is not at all important, that it's actually hurting the whole field, because of course, essentially what you do, the way I like to look at debt, and it's very naive and probably many of the colleagues will disagree, would be just, I typically work with a half space debt because I like the convexity thing, it makes it a bit more tractable. But of course, then if you get a bimodal distributions, a mixture of two Gaussian distributions where the modes are very far from each other, then of course, if you compute the half space debt, it gives you no information or very little information about the actual distribution, actual location of the modes or anything. Simply because it's a quasi-convex function, quasi-concave, meaning that the upper level sets are convex. So there were people arguing that maybe the convexity is not really important. And I even encountered opinions where people essentially justify that anything that could be useful in practice, which to a point, I have a given distribution P. And if I have any function which to a point in the d-dimensional space assigns a number between 0 and 1 or 0 to infinity or whatever, without any additional conditions, they already considered it to be debt because it was fitting very well into the narrative that they proposed some other function which didn't really have the properties of Zorn-Surfling, which was not really robust or didn't have any of these typically assumed properties of a debt, but because it was very nicely fitting into the narrative that yes, we are using debt to produce non-parametric statistics on multivariate data, they were calling it debt. I know that people have been calling the density the debt. It's, I don't know, likelihood debt or something like this. So I really believe that if the field, the whole field of debt, the whole field of these multivariate quantals, or however you want to call it, should be somewhat clearly cut. We first need to really agree on what a multivariate quantal should be, what properties should it satisfy, and what would we expect from a debt to be. Because if there is such a mess that for some the debt could be even a density, for some the debt is only the half space debt, for some the debt is something that they proposed in some paper somewhere, then we really cannot really talk about debt in general, because debt could be simply anything. And I don't know the answer what should be the debt. I'm very sure that this will generate a lot of discussion, especially with specialists, because those are the pursuing these things and proposing new debts and everything. But so my answer is I don't know. I really don't know. I really don't know. It's just that perhaps we should really talk about this and settle this. And this is still only in the finite dimensional case. Now I'll move to the, let's say, functional case where I worked for a while. And there it's even more mess. Because if you start with the usual 4 axioms of Zorn-Surfling, which everybody takes for really of crucial importance for finite dimensional debts, then those cannot really be easily transferred to infinite dimensional case, where actually concepts like, I don't know, local depths, of course, you know what local depths are, you had a paper on that. Local depths gain much more importance in the case of functional data, and they really, I simply have no idea what depth should be. Because there are many papers, there are dozens of papers, everybody proposes their own depth, derive some results, does some simulations. I believe it works. It works very well in certain situations. Each of these depths works very well in certain situations. But then there is this question, where does the word depth should end? What should we still call a depth and what not? And I don't know the answer to this, but it's really an excellent question.
And so I'm just saying this here for the first time. So maybe characterization results might be one way to define the depths, right? So somehow
Yes.
that they find a distribution, something like that. But,
yes. I actually believe that should be one reasonable step. In the case of functional data, of course, it's a little bit more complicated because there you can really have depths which are constant zero everywhere. But yes, that essentially goes back to this characterization. If you really want to have viable multivariate nonparametrics, then the first thing you need to have is that the quantals uniquely describe the distribution. And if they don't, then I really don't know. Yes, but apart from that, that's still extremely weak, right? That's
yeah. And when it's weak, then we don't know exactly. It's very difficult to have general results when we have weak definitions. So that's
yes.
Yes.
Maybe Germain, if you provide the space to Dimitri, if he's here, or if you should continue. I don't know. Dimitri, are you with us? Just to check.
Not sure.
Then
Okay,
yes.
maybe in the meantime, you, Pavlo, you could give your thoughts about this avenues of research.
Yes. So you had So thank you. It's very nice discussion, which also connects the three works presented here. I also like the questions which are distributed, let's say, on at least 3 slides. So these which are like philosophical to different degrees. So these are, I find that they are actually like definitely very philosophical. They're just about directions of studies, those which are presented on the slide we see. So it's difficult to say. I would say everywhere, right? I would say we have challenges here everywhere, right? So coming back to my talk, I would say maybe the challenges can be, it's one way to define the challenges is to define them by the application, right? So if we would like to apply depth somewhere, there we will have certain requirements to this depth, and there we will this will define our applications. This will define the application will define which properties we want from depths, and these properties will cause certain problems, because we will have something which is necessary, which should be satisfied, something where we can take trade-off, and we will also have some budgets in case of, I don't know, computational time, computational resources, memory. So then on your next slide, I think, if I'm not wrong, you were asking the no, maybe then the even next one, yeah. So about the locality of the anomalies, I would say this is a nice question. This is a bit connected, maybe not even just a bit, with the discussion that Stanislav just provided, that yes, indeed. So what do we call exactly depths, and how do we, which properties should it satisfy, right? So do we say, okay, are there global depths and local depths, or aren't they? So not to go like very, very deeply philosophically, I maybe will try to give one more simple example, right? So imagine we want to detect anomalies, right? So I would not say they're always a local nature, right? They can be global, and I would say it actually, the answer on the question, are they inherently local, would depend on application, because actually there are applications where it's very difficult to see anomalies. It's very difficult even to see bimodal distribution, right? And there are applications where distribution is like inherently multimodal, and you can't expect any other development. So here, if you think about, okay, what we can do, right? Once we have, at least my point of view on this is, once we have some kind of, in practice, multimodality, right? This is the case where we would really need add some parameters to characterize this multimodality in practice, right? Do we do density estimation? Do we fit some neighbors like local outlier factors? Do we want to even use the local depths, the one which you introduced? You have this beta parameter, right? Because yes, so there are also depths which would be able to describe probably the multimodalities. On the other hand, if you take something, for example, depth, which in addition has convex contours, right? We are actually in the framework where we do not actually have parameters, right? So we kind of sacrifice certain roughness, but we are in framework where we just have a tool to apply and then see what happens, right? And maybe we will actually already see some anomalies. And maybe the third point in this is that in higher dimensions, right, the situation develops, we start to have different effects, because the fact that the depth is global, right, it does not necessarily say that it will not detect anomalies of local nature, right? You can think of naive examples like two distributions on big distance with anomalies in the middle of them, right? You will see that there is a small group of points distinguishable by their depth values, right? So in this case, you might have choice. Do you want to use local depths or global depths, or maybe some other tool, right? So as I said, the depth is not necessarily always the best tool to detect anomalies. And maybe to answer on the already, because I also don't want to have too much time, and I see that Dimitri is back, so I also want to leave some time to him. Yes, so on this question, I actually think that this is a very important question. I would just add that it's not only computational considerations and robustness, but also other properties. So if you allow me to share one of the slides I prepared in appendix, and which is normally included in the longer version of my talk, which I hope I will give in Prague, where I will be like on Wednesday. If I manage to go through all the manifestations planned for more of it here in France to get to the airport on time. So is this slide, right? So basically what I tried to do here, I tried to classify some of the depth notions, right? And basically you have 3 dimensions of classification here. So I'm sorry if it doesn't coincide maybe with someone's opinion, it can happen, right? It's still, there is always some subjectivity in what I say, of course. So we speak about how can you compute them, we speak about exact computation depths, right? Using in exponential or polynomial in time. Then we speak about robustness of the depth notions, which is in italics there are robust depth notions, in non-italics non-robust. And then also there is a question of affine invariance, very important. For example, in what you asked, robustness and computational time. Actually, there is such a depth. It's called the spatial depth, right? Or lens depth. It will be quadratic. So spatial depth is linear in number of observations, and it is really robust. Its breakdown point of its median is asymptotically approaching 1/2, right? But this is not a affine invariant. As I have shown on the example of simplician volume depth in its non-affine invariant version, it can actually create problems. Where we do not have all 3 properties, right? It's this quarter in italics, right? So basically what we can find anywhere is to have all 3 properties at the same time, right? It's we don't have a depth which would be computable in its exact version in polynomial time, affine invariant, and robust at the same time. And robustness, let's say, we can define it by breakdown point of one of its median of its more central regions, right? So this doesn't exist, and I think it's very important. It's very important question. So I am studying this question currently from more closer perspective, but rather from theoretical point of view, because what I've shown here, it's rather practical part. So maybe I'll finish with another such a thing what we could do in a current application, what I started in some application which we have. We can take a look which properties do we need. And then we would try to minimize the computational cost, for example, to satisfy the properties which we have, right? And maybe we don't need robustness, maybe we don't need affine invariance, right? Or maybe we do need them, but we can sacrifice some precision, right? So this would be maybe my answer, and I'll stop here to leave enough of time. And I'll also stop sharing for Dimitri also to answer. So thank you for your attention.
Thank you, Pavlo. So maybe you can move to Dimitri. Dimitri, do you want me to share the slides again, or do you remember the questions? So the first question was, where is depth going? And then something about locality, and then robustness linked to what you presented.
You're muted, Dimitri. Dimitri, you're muted.
Oh, yes,
Yes.
sorry. Sorry for disappearing so suddenly. My electrical systems just blew up at the very moment Germain asked me to answer, so I had no internet anymore. About where depth is going, I don't have a universal answer to that, although I have a personal opinion, which should not be considered as that valuable. My personal opinion is that I think more and more we shouldn't combine in the same framework depth and quantiles. More and more, I think these are distinct notions. Depth are really useful for geometric purposes, even fine invariance, etc. These are really nice features, but if one wants to speak of quantiles, I think there should be a control over probability content, which none of the depth currently used do satisfy, except from the center outward concept of based on optimal transport developed by Marc Alain. He has a notion of quantiles, which I don't entirely like, but he has a control over probability content, and which for hypothesis testing and for distribution freeness and etc. is unavoidable. But however, depth is really useful in many cases. So I just think these should break path conceptually, I mean. For example, I'm currently working on spatial depth and spatial quantiles. I'm trying more and more to avoid the word quantile. And to join your second question, this is strange what's happening between odd and even dimensions. And at a conceptual level, it should automatically discard this concept that there's such a break in symmetry between odd and even dimension is not natural nor desirable. I have no intuition why there's such a difference. The only intuition I have is it comes from the kernel. It comes from the very definition of spatial ranks with this kernel, which is x over norm of x. And this is this function, which in the Fourier domain makes these power of xi to the power blah, blah, appear. What the consolation I have in mind is that you can just embed a probability measure in dimension 2, for example. You can embed it in 3 dimension and obtain a probability measure with respect to Hausdorff measure on the plane supported on z equals 0, for example. And you can compute spatial quantiles ranks there, but the spatial rank is not the same. For spatial ranks, if you compute it at points on the probability, on the hyperplane on which the probability is supported, you will get the same ranks as in R2. But there are other directions now. There are the... okay, you get it. There is another dimension now. And so the rank function is not the same. So you can recover local results by actually not considering the spatial rank anymore. So I have no intuition. I have not tried to show it on an example, because actually fractal and Laplacian are non-local. So it will never work except on maybe a very degenerate or pathological case example, but it will never work. So this is crazy from my point of view. Maybe there's another way to see this terrible issue. Maybe it's not that terrible. Maybe it's pretty magical that in odd dimension ranks are local. I rather think this is the surprising result, because if you think about it, spatial ranks are convolutions. Convolutions are not known to be of a local nature. So this is probably the odd dimension. This is that is awkward. And your third question was about
the robustness of the...
Yeah, and you talked about you asked me about other directions for characterizations.
Yeah, so do you think in order to get a characterization result, we need somehow a robust measure? Okay, so a very naive intuition, Mahalanobis depth, I mean, definitely does not characterize the distribution. You just know mu and sigma, right? You just know the location and the scatter. So do you think we need somehow to measure a lot of things? And so do we get a robust depth if we need a characterization result?
Okay, so I from the spatial perspective, I would say I understand where this question comes from. For example, if we consider expectiles instead of quantiles, so if the norm is replaced with the squared norm, there is no characterization anymore at all. But seeing it from the Fourier perspective, if we only consider kernels which are location scale families, I don't think robustness is conceptually needed to get characterization result. From the Fourier perspective, as long as I can invert divide by the Fourier transform of the kernel and get something, and as long as the Fourier transform of the kernel does not vanish, this inversion process is possible, and then the characterization result is possible within an extended spatial framework. So I don't think robustness is directly linked to characterization properties.
Yes, thank you. Or maybe just a quick comment to come back on the locality. In the univariate case, the link between quantiles and the distribution is the CDF and the PDF, right? Which is just a derivative, and the derivative is local. So the locality property seems natural, right? It seems like it should hold. And so about whether it's the odd case which is the exception or the even case which is the exception, I mean, I don't know, but at least in dimension one, I mean, we are in the odd case. So of course, so it's, but I mean, my intuition is that locality might be.
So fortunately, we live in R3.
Yeah, exactly. And then the other thing is, so what I had in mind as an example is, so two rank functions which share the same values on let's say an open set, but not in the exterior, and then that would be two different distributions, right? And so having the same rank function on an open set does not mean that the distributions are the same on
yes,
that open.
Of course. And yeah, and to answer to that question again, whether I did not provide an example of this, because it's really complicated to think of distributions which will have the same ranks on an open subset, but will not coincide. Actually, it's to make them coincide over a ball, let's say, which will be complicated. And what should be done instead is to consider ranks and then determine the probability density backwards. But this is really hard to do.
Yeah, I know. So thank you for this. Stanislav, maybe you'd like to add a few things regarding the link between convex geometry and locality, and so I mean, so I don't know. So maybe there are no answers there, but to close the discussion.
It's a bit more difficult as far as I know. Yes, there definitely are some links with some local properties, but it's not so simple. And also, at least as far as I know, some of these properties could be derived, which could be viewed as local properties, but it's more like, for the case of the half space depth, not local properties like local, that they could be characterized by the behavior of the measuring small ball around the point. They are more local, that they could be described as the properties of the supporting hyperplane to the central region. So if you consider a hyperplane to be local instead of a half space, then yes, there are some results, interesting ones, which we are actually working on extending to measures from just these usual uniform distributions of convex bodies. But they are definitely not something extremely simple that could be immediately used in statistics. They're relatively involved. And
Thank you.
regarding the other question about robustness, again, talking about the half space depth, if I look at how these floating bodies are typically used in convex geometry, they are used for the definition of something called the affine surface area. And for that, they only need to consider the volume of the difference between a convex body and some of its floating body corresponding to delta, as delta goes to 0, meaning that it's essentially just the rate in which the floating body fills in the convex body from the inside. And therefore, typical results are only asymptotic as delta goes to 0, which in the case of statistics and measures, of course, transfers to the rate at which the central region expands in the D-dimensional space into infinity. So essentially, these are something which could be translated into results about the details of the distribution. Well, of course, the half space depth is very non-robust, but it appears that it may have some connections with the details of the distribution. And there are some papers where this is used for asymptotic approximations for the convex halves of large random samples, because also the rate at which the convex half of a large random sample expands relates very closely to the behavior of the half space depth. So that's probably regarding that. And if it's a question really about robustness, there would more not search in the literature on floating bodies because there's not much there. I would more focus on other intersections of the depth with other parts of mathematics, such as the concept of measures of symmetry of convex bodies, where measures of symmetry are essentially a generalization of what we call in statistics the half space median or the depth of the half space median, because the depth of a half space median is 1/2 if and only if the measure is symmetric in some sense. So essentially the depth of a median somewhat describes the symmetry of a distribution. And there are results about this in convex geometry for convex bodies. Or perhaps I would go into discrete geometry, where they have a wealth of results about so-called center point theorems, all kinds of variants of that. And those are essentially results about the half space median and about robustness, but not necessarily in floating bodies.
Yes, thank you. That's what I had in mind to do with respect to the median. Okay, well, thank you very much for this discussion. Maybe we can open the debate to everyone. So, are there any questions in the audience?
If anybody has anything, please just unmute and ask us. We are now exactly 16. Audience. I will start with few questions of my own, and please others in the audience also ask questions then. Actually, I have 3 questions based on the presentations. Firstly, broadly for all, I would say in general, the speakers and Germain. Firstly, can depth, I mean, in which situations the depth concept and depth functions can be used to replace, as you mentioned, either quantiles, ranks, or just general, I would say, modeling criteria or distances, which are used in regressions, in dimension reduction, in anything? Is this robustness, or is this any other criteria that would be beneficial to use depth? I know that there is depth-based regression and other modeling. So where is actually depth? Is there any criteria or findings? Where is it preferred? Just for general, I would say statistical practice. Secondly, again, possibly philosophical or extension, could depth be translated, say, to complex objects, to manifolds? Functional data was actually mentioned, so just to any, I would say, object, mathematical object, also maybe topological related data. Could some of those concepts also be used there? This broadly relates to, as Paolo was mentioning, machine learning aspect and so on. This is more a specific question. You compared, I think, depth related anomaly detection and machine learning, few machine learning approaches. Could depth be combined with, say, neural network perspective? Probably this is already something known, but just a question. Thanks this much, Justin. My side.
Yes, I don't know if I should start or if someone else wants to answer first. So the first question was about applications of depth mostly. So the most successful field in which depth has been applied is supervised classification, right? So where you want to assign a point to a population, knowing that depth somehow measures centrality or can measure something else, then you can assign points to one or the other distribution. So that's the main field of application, let's say, of depth. And well, because depth mostly measures centrality, any question that relates to that, it can be useful, right? You mentioned other fields of interest. I forgot already.
Like regression or just general modeling.
But so regression depth, it's a nice definition, and there's been some use of that in the sense that it is a robust depth measure, so that you get a non-parametric estimation of the parameter in the regression model, but it's extremely complicated to compute, and so it takes quite a lot of time. There's been some extensions, and that relates to your second question. There's been some extension of depth in two directions. First, in order to measure the depth of parametric parameters in parametric distributions, right? So whether a regression line is appropriate with respect to some data. And there's been some recent papers extending depth to other more complicated spaces. So Stanislav mentions functional depth. There's actually an intense research in that direction, but I saw some papers on depth on manifolds, on topological spaces, etc. So that's starting to come. So depth for complex data. When it comes to the neural networks, I think Pavlo might be the best person to answer this question. I personally don't know, but maybe he knows. So I don't know if anyone wants to add anything to these answers. Pavlo, maybe you know something in the neural network community?
Yes. So maybe yes, I can answer on this specific question. So. Yes, there are definitely connections, or one can find connections, right? So first of all, for example, if you speak about anomaly detection, the topic of my talk, as I've shown there, I can see them, the neural networks and the data depths, as two complementary methodologies, right? Because there are tasks where neural networks will be better, there are tasks where data depths will be better, right? So this may be one point of view, but one should not also forget about another point of view. It's okay, when we have neural network, it's basically some fixed model which we need to fit, and for this fit we need learning. And when we use some kind of learning, right, algorithms, we need some risks, and based on these these risks will have some losses inside, right? So here until now, so this is something interesting, something I think I've already written told other people several times. We always see this as these risks. There is usually one quantity, right? Something happens, and maybe there are several losses connected to that, or the risk is weighted sum of some losses, right? And this reminds me this idea of also risk estimation in economics, where we have been we were speaking. Okay, we try to put everything into one property, to one variable, like money, right? Using some transformations, like usually currency exchange, right? We express everything in dollars and we apply univariate risk measure. And of course, it doesn't work that well because we do not have in the real world full substitutability of the goods, right? Because we also have some transaction cost, right? So this doesn't work. And then one of the applications of data depth is actually multivariate risk measure, right? So then the question is, could we, for example, use the same idea for the risks and losses of neural networks, right? Because until now, what we are trying to do, we always have something univariate on the output and we fit it. But if we manage to compute the multivariate criteria to fit neural networks, maybe we can get better models even in that. And maybe one small application where really two things were fused, which I can speak about is, so, I mean, neural networks actually, today it's a big tool, which is used like everywhere and which solves a lot of tasks. And I also hear already questions, will neural networks, so even like stated in extreme way, will neural networks eliminate statistics, right? I would say I rather am pretty sure in negative answer on that, right? But so neural networks has many problems. And one of them, the one I was already speaking about, is interpretability. And I actually also do work in that direction. We try to provide interpretability, explainability of neural networks. And so one example where actually data depth was useful. So since we now can compute it, actually we try to compute it in larger dimensions, even up to hundreds, right? It just takes a little bit of time, but also not that much if you run good approximating algorithms, which are optimization nature, not purely random. And so what we have done, we have some class of objects, and we have, I think it was like, for example, apples, and then we explain why neural network thinks it's apple. It will say this is round type object which has some like spot on some side, maybe like this green apple, some red spot, and it can have with high probability some small piece of branch and maybe one or two leaves, right? And then we explain, and there are several objects in the data sample which we could not explain. Visually, we could identify that they just don't look like apples, right? Just because, right? These were kind of outliers or anomalies. And then when we did apply the data depths, it actually turned out that they are detected as anomalies. So it can be done in an automatic way that we can say, okay, if this is something which we cannot interpret a neural network, the data depths will show you that these are anomalies. And this is actually pretty fine that we cannot interpret it, but it's because it completely doesn't fit in the logic of this class, which were fitted by the neural network. Yeah, so
okay.
This will be my answer.
Thanks for a very thorough answer. Thanks. We have a question in the chat from Gargi Roy. Gargi, I will ask it myself, or you can unmute. He asks, is it possible to show examples from what is depth section of Paulo's slides? Paulo, maybe we skip this, but if you maybe really shortly comment.
Okay. I mean, it's like, it's not, there is nothing I can quick show. There is not much to show there, right? So I just have shown another example. So these are the postulates about which we were speaking. This is what we demand from data depths. And these are about which we had discussion. These are usually, so I will not go in detail. There are properties which we ask to data depths, but I agree with Stanislav. Also, I think Germain also expressed his opinion on that point. It's questionable whether it's a correct properties. And also another question, in which space these properties are appropriate or not. So I think it's rather source for discussion today. They should not be necessarily taken as granted. If you want to look at pictures, it's just what Stanislav has shown. It's to how to compute depths with such a hyperplane, which minimizes a fraction of points in this hyperplane. And this is a depths computed for every single point of the example, where the sample points are projected from above as the red dots on the surface of these depths. And then this is just what is region, Tukey region. And then I have shown the same thing. It's contours of the depths computed in 3 varied space with 2 sources of light, yellow, and blue. So nothing particular, just an attractive visualization. And you can see the 3D nature of the data, the scatters, the shape of the data. And in the middle, you have this stone. It will be the Tukey median. Or if you want 1 point, you can take the center of gravity of this stone. And I think that's about it, about these slides. Yeah.
Okay, thank you.
I hope this answers the question.
I hope. Thank you. One more question. I have possibly others. We are probably at the end, but we have enough time. Stanislav mentioned, naturally discussed convex geometry and relationship to convex hull and so on. To my mind, and this relates surely, say, to Dimitri's talks as well, to which extent is research on depth connected to stochastic processes and probability? Could this be linked, say, to random geometry, which is so much discussed today, related to works of Scott Sheffield and many others? So what is the connections here? is it possible? Dimitri discussed naturally differential equations and so on, fraction operators. To which extent could this be connected?
If I may answer, there are definitely several fields of mathematics where the depth connects. And what I can really comment on is especially this half space depth, which I have been really looking into this. And there are actually many connections. It's not only convex geometry. As I said, there's a lot of results in discrete geometry, which are concerning the situation where you don't really compute the depth of a probability measure like a theoretical, the density, but only a random sample. Then, of course, you have a lot of results on this in discrete geometry, in computational geometry. You have results from basically functional analysis about these measures of symmetry. And there are results from differential equations. There was a very nice paper of, I don't remember the names, but it was about connections of half space depth with some PDEs somewhere, where really the half space depth turned out to play some special role. And there are definitely additional connections, not only of the half space depth. I can also comment on connections of other depths, like there exists the zonoid depth, which is a completely different notion. And it also connects quite a lot, for example, with functional analysis, with theory of positive definite functions, a lot of this. So I believe that this is a field which really needs to be explored. There are a lot of things to uncover, and we are just in the beginning. But definitely there will be a lot of things to gain also today. The idea of depth in statistics.
Thanks. Thanks a lot.
I agree. Just to comment on Stanislav's comment, I totally agree with him. And for example, if you consider stochastic processes in which some parameters, unknown parameters are involved, for example, I don't know, time series or ARMA models and so on, you have unknown parameters you want to estimate. And in this context, if you do not assume any model if you do not want to assume any specific model generating the stochastic process you observe, in this case, you can definitely use some concepts of data depth. And here, distribution freeness with respect to of the statistics you use to estimate parameters should be very important if you do not want to make assumptions on the underlying model. Even in parametric cases, not functional ones, even in parametric cases, having no distribution freeness of statistics, of test statistics you use may show bad behaviors and bad things to happen. But this is the kind of things you could definitely do with the stochastic processes, even with data depth and without distribution freeness. But these are things that are done today.
Great. Thank you. Thanks a lot. I was answering to Nina. Nina, you also have a question.
Hi, everyone. Thank you very much for the great talks and discussion. And so I typed my question in the chat, but since I'm here, I was in doubt I will be able to join until the very last moment. I wanted to ask whether there is a connection or whether this data depth notion can include some aspect that takes into account the density of a distribution or the density of some points. So, for example, in density-based clustering, you'll take into account a sort of local density that you have within your data points. If this can be included in the data depth notion, maybe, since I see that there is a big issue of multimodality, it may be that with only a data depth notion, you will not be able to take into account multi-modes. And for example, you will consider a mode if it will be lower in terms of density as an outlier cloud of points. This is my intuition based on the data depth, which I'm quite new into this topic, but this is one of the major issues I can see here. Maybe if you account for the density, then you will be able to categorize that cloud of points as not outlier points, but as part of the main normal data. So I don't know if it makes sense at all.
No, I can answer maybe. And so thank you very much for your comment. Yes, I can answer. Okay. So that's a very interesting question, and actually, so there are some works, and I did some work in trying to define a local version of depth, something that would be multimodal. Half space depth, if you look at it, it's always the depth is always going to be unimodal, right? So it's from the center and then it decreases. And so if you have elliptical distributions, there's a one-to-one relationship basically between the depth and the distance to the center, the Mahalanobis distance to the center, let's say. And that's not true in general. And so I've had discussions with other people, and including Stanislav, Pablo, and Dimitri, about whether depth should be equivalent to density or whether you should be interested in measuring something different. And indeed, if you have a multimodality problem, then maybe you should get away from those classical definitions of depth because they're not appropriate for that. And if you know what you're interested in is the density, then you should go for it. If you're interested in something else, then maybe you could capture that something else using a depth function. That's the whole debate.
Thank you.
Great. Anybody from the speakers as well?
I believe that the basic kind of paradigm of the depth, at least the classical depth, the one that prime representative is this half space depth, is that unlike the density, the depth should be global in a way as the quantiles are global in the one-dimensional case. Because if you want to look at the median, then you really need to consider the whole distribution and not just the small neighborhood of the median, because from that you simply cannot determine whether it's a median or not. So at least if we talk about depths in terms of multivariate quantiles, I believe that the idea is that they should be global. They should be more like this half space depth, less like the density. But of course, that doesn't mean that the combination of a depth and a density would not work very well in practice. And I believe that that could be a very good idea, and people definitely tried it a lot. So this is, again, kind of a conceptual question. What do we want to call depth? Thank you.
Okay.
I have a personal opinion on locality, which is quite different from what Stanislav just said, and which joins your question about manifolds earlier. In a Euclidean setting, I would agree that quantiles, ranks, depth, and so on should be global to some extent, because, okay, these are just extensions from the univariate case. But if you consider manifolds, they have strongly different topologies and shapes. And for example, if you consider the sphere has a really different behavior than a Euclidean space. It actually is too symmetric. It has too many symmetries in it. So for example, if you consider a uniform distribution, the uniform distribution over the sphere, I cannot picture what a global quantile or depth notion on this very symmetric object would look like. And this phenomenon is not possible over Rn, because you can have a uniform over the ball, but the ball is not the whole space. And you cannot precisely have a uniform probability measure over the whole space, which is possible in compact manifolds such as the sphere. So in there is no unique median. Actually, any point of the sphere, if you have a uniform distribution, is a valid median. If you have, even if you do not consider uniform distribution, if you have a distribution that is that has symmetries with respect to antipode, where I don't know how to say, which is symmetric with respect to reflections. So X has the same distribution as minus X. Then any median should have an opposite counterpart. And so each depth concept or quantile would be symmetrically defined at both ends of the sphere. So in non-Euclidean setting, I think the global paradigm should be avoided. And this asks the question, seeing Rn is a particular manifold, shouldn't we be looking for non-unimodal concepts in Rn and thus deviating a bit from the usual CDF and the usual quantiles concept? That was my view on it.
Yeah, I could just add that I completely agree that once we leave the Euclidean setting, probably the convexity or the global nature simply fails. And it completely fails already for the case of functional data, infinite dimensional data, that it doesn't make any sense to even require these things. So yes, I completely agree. Maybe really these quantiles in terms of global depths really do have meaning only in the Euclidean case. It's quite possible.
Okay. Is there any further question? If not, I again greatly thank to all three excellent speakers, Germaine, naturally, for all the help and great discussion, and helping the organization, all the participants, I would say, for a very, very lively discussion again. At the seminar, I also announced next seminar is in October. I think it is October 9th. On recent advances in model specification in different data structures. Some of it will be, I think, related to some of the issues related, say, to functional data or similar that we discussed today. So again, thank you to all. The webinar, as mentioned, was live streamed and recorded, and it will be almost immediately accessible online. Thank you, and hoping to see you soon on any great event in statistics and related areas. Thank you. Goodbye. Thanks to all.